2, 1. Alright. Okay, so we got one more thing to talk about when it comes to differentiable functions, broadly speaking. I mean, when we get to integration, we'll, of course, talk about derivatives as well. As we know, differentiation and integration are intimately related. But we've got one more thing to talk about, and it's a very famous theorem about differentiability and invertibility. Now, you may not have heard of this before, but you know what this is. So remember in calculus, the following is true. If I have an invertible function that is differentiable, then the inverse remains differentiable, and the derivative of the inverse is found via the following formula. The derivative of the inverse is 1 over the derivative of the inverse. Okay, right, and recall that while we do learn this, kind of the real power of this is that this gives you a way of figuring out derivatives of inverse functions based off of the derivative of the original. So, for example, because we know that e to the x is its own derivative, this tells us that the derivative of log is 1 over x. Right, and this is also useful in giving us the derivative of arc sine, arc cosine, and broadly speaking, if you have an invertible function, you want its derivative, you can apply this formula. Now, right, when we were talking about derivative rules, we didn't introduce this, because it turns out that this is not so cut and dry. Right, so in calculus, we tell you the derivative of a sum is a sum of the derivatives, the derivative of a scaled function is a scaled derivative, the derivative of the product is the derivative of the first times the second, plus the derivative of the second times the first. Then you get, the quotient rule, high D low, low D high, low low, yeah, good stuff. The chain rule, derivative of the outside, leave the inside alone, multiply the derivative of the inside. And all of those are basically as true as they were in calculus, and the proofs are more or less the same with a couple of minor little points. Chain rule is a little more complicated. This derivative rule that we learn on the other end, however, it is somewhat shocking that this does not go as smoothly as those other rules that we learned. Right, the proof of this, there's some things here, and now you may be going, well, wait a minute, I remember a proof of this in calculus. It's super easy. F composed with f inverse is equal to x. Take the derivative of both sides, and then boom, solve for the derivative. I'm done. How hard could this be? Right, and in fact, the other proofs, like the chain rule, of course, that proof's a little wonky, it has a little spot where you kind of cheat. This seems just straight up like, hey, speaking of the chain rule, bam, hit the chain rule. You're done, dude. How is this hard? Well, note something. This assumes that the derivatives, the inverse, has to be differentiable. So note, if I know that the inverse function is differentiable, this gives me the formula. But note, this argument is only good if you know this is actually differentiable to begin with. And so that's the actual question. If I have an invertible function and I know it's differentiable, must the inverse actually be differentiable? If it is, then I've got a formula for it, and great. So while this is nice, and you see this in calculus, right, we kind of lie in calculus because we're just like, oh, everything's differentiable, whatever. This reveals, oh, wait a minute, we got to be a little bit careful. And quite shockingly, there's some roadblocks here. Okay. So before we go full bore and get into this, let's first address the question of continuity. So specifically, let's say I have a function from a to b, subsets of the real line, and I know it's continuous, and I know it's invertible. Does it follow that its inverse must be continuous? This is a pause the video moment. And try to and think about it. Don't spoil it. Think, is it possible? Well, sadly, the answer is no. And it's actually not too hard to see why, because, as always, piecewise functions do a pretty good job of ruining pretty reasonable sounding theorems. This function right here is nice and continuous. Its inverse, however, has a discontinuity at 1. It jumps from 1 to 2 at x equals 1. It's not continuous, unfortunately. Views. Big views on that, unfortunately. So, continuity, it turns out you can lose it when you invert. And this is a pretty good example of a natural question of if I have a function and it has a property and I know it's invertible, does the inverse have the same property? A lot of math is devoted to that. It turns out that some things work better than others. So, for example, strictly increasing carries over with invertibility, so, you know, that's a good thing. But there are some things that don't. Continuity is one of them. Now, note, this is indicating that if this was true, differentiability would be preserved over invertibility, and I am sorry to report that Paris is burning after all. It doesn't immediately follow that the inverse needs to be differentiable, unfortunately. As we will see, there are some subtleties, as always. But before we get there, what we'll do is note that while the inverse of a continuous function may not be continuous, it turns out, and if you have a little bit of an eye for it, note what the domain was. Yeah, we don't like sets that look like that. We like nice, non-degenerate sets. Okay, so it turns out that the problem is if you've got a weird domain, you can have a continuous function that fails to have a continuous inverse. However, if the domain is an interval, a non-degenerate interval, then the inverse has to be continuous, so continuity is preserved in that sense. And furthermore, we'll kind of stick with that to ensure differentiability is going to work. Okay. All right, so side note here, this is a material that's out of 3.6 out of the book. We're kind of double dipping with chapter 4 and 3.6 here. I didn't want to do 3.6 and then talk about derivatives first. I wanted to do derivatives and then when we need the 3.6 stuff, which is this material. Okay, so first things first, we're going to prove a couple of nice facts about continuous functions defined on intervals. So first of all, their range is an interval, which is a fact that we're going to use quite a bit. And furthermore, if I have a continuous and injective function defined on an interval, then it's got to be strictly increasing or strictly decreasing. I highlighted and said the opposite. Yeah, so it turns out that if you're continuous and injective, you only have one of two choices. You're strictly increasing or strictly decreasing. That's it. No more, no less. Okay, so that's kind of, and if you try to envision that, right, if you're defined on an interval and you're continuous, and I know you're injective, so you can't repeat values. And since we're continuous, the curve needs to draw out continuously, and it's 1 to 1, so yeah, it's got to always be moving up, or it's always got to be moving down. I highlighted it backwards again. Moving on up, moving on down. The reason I have decreasing first here instead of increasing, which is how I normally write it, is note this is an or statement, so we're going to suppose this doesn't hold, then this must hold. That's how we're going to do the proof. Alright, well, first things first, let's prove that the image of an interval under a continuous function remains an interval, and this is just restating the intermediate value theorem. So pick two elements in the range, okay, and then pick an element that lives between the two. Alright, there are A and B, so that f of A is equal to Z, and f of B is equal to W. Y lives between them. Intermediate value theorem gives me a C, so that Y is equal to f of C. There you go. Alright. So that's all I have to say about that one. Beautiful. Okay. Alright, so that's point 1. Point 1's kind of straightforward and easy. Point 2 is not that hard. It's slightly tricky. And it involves a couple of clever applications of the good old intermediate value theorem. Right, like I said, if you think about a continuous function, if it's injective, it cannot repeat values. So if it was not strictly decreasing, well, then it's got to bend somewhere. And because we know continuous functions obtain intermediate values, yeah, no, that can't happen. You have to either be always going down or always going up. Now note, this puts a pretty big restriction on continuous injections. So for example, polynomials, if they're injective, they have to be strictly increasing or strictly decreasing, and that sort of immediately throws out a lot of your options in terms of what your polynomial can be. So for example, note it does not have any minimums or maximums, so its derivative is not equal to 0. So, okay. Anyway, let's keep going. Alright, so suppose, so we're going to prove that if f is continuous and injective and it fails to be strictly decreasing, then it must be strictly increasing. Alright. So, since it's not strictly decreasing, that means there are A and B, so that A is strictly less than B. but f of a does not exceed f of b strictly. Alright, now note, a and b are not equal to each other, and since f is injective, this has to be a strict inequality. If this was an equality, then a would equal b, and oof, I'm a goof. Alright, so the first thing we're going to verify is that f of a is less than f of x for any x in the interval I that's bigger than a. And likewise, f of x is less than f of b for any x in the interval that's less than b. And as always, I'm only doing half the work. If you want to do the other half, you do that on your own time. It's, again, it's identical proof, change inequalities, and change some symbols. Alright. Anyway, so pick something that lives in the interval that is less than a. Alright, and for contradiction, suppose that f of x is less than or equal to f of a. Alright. And again, note that we have to have f of x is strictly less than a, x is strictly bigger than a, so inequality cannot hold due to the injectivity. Now, f of a is strictly less than f of b, so that means f of a would live between f of x and f of b, so by intermediate value theorem, I can find something between x and b. Remember, between x and b, so that f of c equals f of a. But by injectivity, f of a equaling f of c forces c is equal to a, and then we get, once again, our all-time favorite contradiction, a is strictly less than itself. And there we go. It's got to be that f of a is strictly less than f of x. So, clever application of both intermediate value theorems, so the hypothesis of us being continuous and living on an interval. Furthermore, the injectivity jumping in and helping us out. Okay, beautiful. Right, so specifically, again, the x needs to live between the two, right, because we can focus our attention to the interval x to b, and intermediate value theorem guarantees that it lives there, and yeah, there we go. Alright, 10 out of 10. Okay, so now that we know this, so note, this kind of implies that we should do, right, this gives us basically two pivot points to work from. Right, I know that f of a is strictly less than f of b, and now I verified that, alright, anything bigger than a is going to remain bigger than f of a, and anything less than b is going to be less than f of b. So now I just need to kind of use this to guarantee that strict increasing is happening everywhere. Alright, so pick x and y to live in I, and let x be strictly less than y. Alright, I want to show that f of x is strictly less than f of y. So, again, for a contradiction, suppose the opposite. And again, note the injectivity guarantees that it has to be strict. Alright, there are two cases now to consider, and they rely on where x is in relation to b. Alright, if x is strictly less than b, as we proved, that would mean that f of x has to be less than b. By as we proved, I mean the thing I said was true, and you better prove it. Alright, so we know that that holds, but now what's true? F of y, strictly less than f of x, strictly less than f of b, so there's some point c between y and b, so that f of x is equal to f of c, but then injectivity gives me that x is strictly less than itself. Right? X is less than y exists beyond, exists beyond y, alright. But by the construction of the injectivity, we get that they're equal. Alright. So now the other condition is, alright, well, let's suppose x exceeds b. Then, we know a is strictly less than b, which is less than or equal to x now, and less than or equal to y. So, that forces f of a to be less than y, which means f of a is less than f of x, and f of y is in between. So there's a c between a and x, so that f of c equals f of y. Injectivity then gives us our favorite contradiction, and there we go. It's got to be that f of x is strictly less than f of y, because otherwise we run into some contradictions. And there we go. Any continuous injection defined on an interval must be strictly increasing. The end. Good stuff. Alright. Cool. Alright, now let's let's let our minds float back to why we're talking about this right now. We're investigating the question of when does continuity carry over to the inverse of a function. Okay. And the reason we're talking about that is because we're trying to address the question of when does differentiability carry over to the inverse of a function. And, okay, so what we've just proven now, though, is that every continuous injection is strictly increasing. Okay, what does that have to do with the inverse being continuous? Well, a couple of things. So, first of all, any strictly increasing or decreasing function must be injective, and thus it has an inverse. Okay, not too shocking there. What is shocking, though, is point 3. Point 3 is probably one of the most shocking results, I think, in analysis. I think every course, actually, now that I think about it, I think every course is going to have that one theorem. That one theorem that is just, no way. Yeah, just that one statement you're like, there's no way that's true. No way that's true. Right? Right, so for linear algebra, the one that I've always hated in linear algebra is that the determinant of a matrix is unaffected when you scale a row and add it to another. That is shocking that doesn't do anything to the determinant. Now, I know why it works. I've proven it, and, you know, and there's a bunch of, like, physical interpretations you can do if you think about determinants as, like, areas of parallel pipeheads and shit like that. But it's still just the mechanics of that. How does scaling a row and adding it to another not ruin the determinant? You know, like, the determinant's such a disgusting formula. How is that, you know, respected? So for analysis, I think an equivalent thing in that regard is this. If you have an interval and a function that's strictly increasing on it, its inverse is continuous, guaranteed. No, f does not need to be continuous itself. It just needs to be strictly increasing. Right, since we're strictly increasing, we have an inverse. And note, I is an interval. It's not an interval in 1 or 2. Note of that, please. So, very shocking that this is true. We're going to do so our textbook proves this in section 3.6 out of the book. We're going to do a completely different proof. I quite honestly, I like Lebel's book for the most part. Like I've mentioned, I've talked to him a couple of times. I think next time I email him, I might just be like, dude, rewrite section 3.6, it sucks. Section 3.6 is probably the weakest part of the book, in my opinion. Somebody forward him this video with this timestamp. Anyway. Yeah, so we're going to do a very different proof. And a proof that I think is a little bit more direct. He does it with talking about when our monotone function's actually continuous. Which is yeah, sure, whatever. Anyway. Alright, so like I said, this is an incredibly shocking result, the fact that this is true. And what's nice about this, and then no, it doesn't matter if you're increasing, it can be decreasing as well, as per usual. So what's quite shocking about all of this is that, well, this is the shocking result. So this result, in combination with the other, which is that any injective continuous function is strictly increasing or strictly decreasing, this guarantees that if you have an invertible continuous function defined on an interval, its inverse is in fact continuous. So there we go. So continuity does not necessarily get preserved under invertibility, under inversion, but if the domain is an interval, then it does. Okay, so that's the goal. Alright, so point 1, first of all, strictly increasing means adjective. Alright, so let's say we have x and y, so that f of x is equal to f of y. Just need to prove x is equal to y. Alright, well, if x is strictly less than y, then our hypothesis gives f of x is strictly less than f of y, which can't hold. We're assuming they're equal. And likewise, if y is strictly less than x, we get the same issue. So it's got to be x is equal to y. By trichotomy. Boom. Boom. Okay. And point 2 is proven similarly to point 1. Okay. Alright, so let's prove now the inverse function of a strictly increasing function defined on an interval is continuous. So like I said, the kind of the star of the show for today, and maybe even the course, the theorem that is the most shocking. Just a straight up, no way that's true, bruh. But it is. Okay, so no, the domain of our inverse is the range of our original function, so f of I. Alright, so pick an element and pick an epsilon. I just gotta find a delta. Alright, so how we're gonna go about finding that delta. So first things first, note that since w is in f of I, that means w is equal to f of a for some a, and then note, by the way inverses work, that means a is equal to f inverse of w. Okay, so first things first, so note the hypothesis said interval. It didn't actually care about the degeneracy of it, and that means, well, we kind of do have to actually break it into the two cases of, well, what if the interval is degenerate? If the interval is degenerate, that means it's either empty or has only one element, and we know something's in there, so the interval just has to be a, which means that if I take any y that's within 1 of w, well, then y has to equal f of a, which means y... f inverse of y is a, and yeah, then trivially we get continuity. Alright, so we can now go ahead and assume that the interval we're dealing with is non-degenerate. Alright, now here is a little bit of a frustrating spot in the proof of this. So we now hit the point where things break into 3 cases. And guess what? I'm only doing one, and you get to fill in the details on the other. So what are the 3 possibilities now? So A lives in I, and if I is not degenerate, that means there's something else in I, and depending on what else is in the interval is going to affect how the proof goes forward. So there are 3 possibilities. A is the minimum of I, and there's something bigger than it. A is the maximum of I, and there's something less than it. Or there's something bigger than it and something less than it. And being the rat that I am, I'm only going to do the 3rd case, and the other 2 are treated similarly. And I'll explicitly point out the difference, because there's only really one difference, and it involves what delta is going to equal. So if A is a minimum, or if A is the maximum, it'll affect what delta is, and that's really it. So I'm going to prove the 3rd case, because the 3rd case is the one that has like the most going on in it, as we'll see. Okay, so the other 2 cases you can fill in the details if you're so inclined, and once you see the 3rd case, you've seen the 1st and 2nd, so let's do it. Okay, so we are now assuming, furthermore, that there's something to the left of A, and something to the right. So I'm going to define nu to be, eta to be epsilon, and then a minus r over 2 and t minus a over 2. So again, r is to the left of a and t is to the right of a, so this is positive, so is that. Note, eta is positive here. Okay. Now what are we going to do? Alright, now we're going to do our favorite little trick. We're going to subtract eta off of a, and we're going to add eta to a. Okay. Alright, so note that r is strictly less than a minus eta, which is strictly less than a. A plus eta is strictly less than t. Okay. Now, since I is an interval, and r and t are in I, that means a minus eta and a plus eta live in my interval. Okay. Now, for right now, this part and this part maybe make a little bit of sense of, oh, I gotta sneak them in. The epsilon right now may not make too much sense, but trust me, bro, it's going to. Okay. And note, in addition, since I have a minus eta less than a and a less than a plus eta, we are going to have the strict inequalities here as well. Okay, so far, right, what's the difference when, let's say, we know a doesn't have anything to the left of it? A is the minimum. Well, if a is the minimum, then we just don't include this. And so my eta is just this and epsilon. And so this whole part I don't care about, right? And I don't care about a minus eta because it just straight up doesn't exist. Yeah. And likewise, if a is the maximum, then there's no point doing this part. All right, so this part doesn't exist. All right, so going forward, what's going to happen now? Because, right, so far it looks like, some, analysis happened. And, right, the magician put the person in the box, and now we're waiting for, you know, them to come out. Like, well, what's going on? Alright, well, here's what's going on. So now we're going to set delta equal to the minimum of these two quantities here. And note delta is positive by construction. So again, note here, so note, we have our delta. So given an epsilon, here's the delta we want. And if you're looking at it going like, why the hell does that work? You'll see. Alright. Now note, again, the difference if we have, let's say, f of a is the minimum, well then you don't have this, so then you just take delta to be this. So there's no minimum process here. And likewise, if f is the maximum, then we don't have this thing, so you don't include this. You just have that as your delta. So it's the only difference. Right, like I said, there's marginal differences between the three cases. Alright, so finally, let's wrap things up here. Let's take y to be in f of I, so that y minus w is within delta. Okay, now, alright, how is epsilon showing up here? Well, here's how epsilon showing up. Since y is in f of I, that means it's equal to f of b for some I that lives in b. Now note, f of b minus f of a has to be less than delta. Right? Y is equal to f of b, and w is equal to f of a. Delta was chosen so that... Oh, look at this. This guarantees that f of b minus f of a is less than delta, bigger than negative delta, but delta was chosen so that delta is smaller than this, and smaller than the negative of this, so the negative of it is bigger. And now, add f of a across the board, and we get f of b is stuck between these two. Now you might be going, well, alright, I'm stuck between those two. What's big whoop? Oh, it is a big whoop. Alright, so, note, if b was less than or equal to a minus eta, by the fact that we're increasing, we would reverse the inequality I know to be true. So that cannot hold. And likewise, that can't hold either. So it's gotta be that a minus eta is strictly less than b, which is strictly less than a plus eta. Subtract a across the board. Now we have b minus a is strictly less than eta, and eta was chosen to be smaller than epsilon. Boom! F inverse is continuous. Look at that. Look at how slick that proof is. That is a, ooh, that's choice. It's a good one. Contradictory. Yeah, some of these spelling mistakes, they're pretty good. They're pretty choice, gotta say. Contradictory. My, so this is my home computer that I'm doing this on, not my work computer, and the keyboard on my home computer is a little janky. It's not the worst thing ever, but anyway. Oh my god, what's going on? What's fob? Foe of B showed up. There we go. Okay, so hey, not a bad proof, right? Kind of a really slick proof, the way it all works out. This is a great little, like, magic trick. I love this one. Right? It starts off with this nonsense, you're like, alright, where's this going? And then even when you get the delta, you're still kind of like, I don't know. But then when you get here, right, when you get here, like, then all of a sudden it's like, ooh, hoo. It's a good one. It's pretty cool. Right, and again, note, all we used I was an interval. We used my function for strictly increasing. And that is it. Right? And again, that's all we have. We're on an interval and we're strictly increasing. Using those two together, we were able to prove the inverse has to be continuous. So cool. Right. Yeah, so like I said, pretty straightforward proof. Not too bad. And you know, our textbook does a very different proof that's built off of when monotonic functions have to be increasing. So as I've mentioned, we didn't prove this, but you can prove it. A strictly increasing function is invertible, and its inverse is also strictly increasing. But anyway. Alright, so, point 4 was same theorem, but strictly decreasing. Similar proof. And now, finally, for point 5, since we have a injective continuous function. If it's strictly increasing or strictly decrease, it must be strictly increasing or strictly decreasing. So 0.3 or 0.4 guarantees that the inverse is continuous. And there we go. Continuity unaffected by inversion, as long as the domain's an interval. Cool. All right, so we answered the question now for when does a continuity not get ruined by invertibility. Let's now answer the question for differentiability. All right. So it turns out that we roughly get a pretty equivalent statement to when invertibility works, when continuity doesn't get ruined by invertibility. So here we see a theorem for differentiability that more or less works, but if you got a keen enough eye, you might be noticing something about it. All right, so let's take a non-degenerate interval and a differentiable function, as per usual. And note my assumption. I'm not assuming the function's invertible. I'm assuming it's got a strictly increasing derivative. So if my differentiable function has a strictly positive derivative on a non-degenerate interval, then its range is non-degenerate, the function itself is invertible, and its inverse is differentiable, and it's precisely what it should be. The formula that we've already seen. And likewise, if the derivative is strictly negative, there we go. So, note, there's a little bit of a subtle difference here. Right, we're not just going, oh, I've got a function defined on an interval, and it's differentiable everywhere. Now, of course, the derivative needs to be non-zero in order for this formula to hold. But note my assumption here. I'm forcing it to be strictly positive. And there's kind of a reason that we got to do this. We'll talk about it in a little bit. But before we do that, so let's prove it. Alright, so let's prove that if I'm differentiable, and I know that my derivative is playing nice, then I can guarantee that I have a invertible, my derivative is invertible, my inverse is, my derivative is invertible, my inverse is differentiable, and the formula that I want to hold holds. Alright, so we got a couple things to prove. First of all, the range is a non-degenerate interval, the function itself is invertible, and its inverse is precisely what we want it to be. And the derivative of its inverse is precisely what we want it to be. Okay, and you know the deal. Okay, so first things first. Since my derivative is strictly positive, I know I'm strictly increasing, so we've got to be injective. Now, since I is an interval, and my function is differentiable, meaning it's continuous, its range is an interval. Our hypothesis guarantee is that there are A and B and I that are distinct, so the injectivity of f ensures that f of A and f of B live in the range and are also distinct. So, point one, the range is a non-degenerate interval, so we can talk about differentiability. Alright. Okay, next up, let's say, now, since f, as mapping from I to its range, is injective, it must be an invertible function. Moreover, f is strictly increasing, so it follows that the inverse is continuous. And here's the spot. So your brain might be going, well, wait, why are we assuming the derivative is positive everywhere? Don't we just need the derivative to be non-zero? Nope. Because if we have non-zero, we don't necessarily have this is continuous. And if it's differentiable, it must be continuous. And that's kind of the problem. So, we'll talk a little bit more about this, but for right now, if you're kind of wondering why are we assuming the derivative is always strictly bigger than zero, here's the exact spot in the proof where we need it. Alright. Okay, so finally, we got one more thing to prove. F inverse is, in fact, differentiable at every point, and the formula for its derivative is what you want it to be. Alright, so note, f of I is a non-degenerate interval, so y is a cluster point of it. And likewise, y is equal to f of x for some x, and x is also a cluster point of I. So, right, I'm allowed to take limits at these things, and we're going to prove that the derivative exists, which means that a derivative and is equal to what we expect, which means we're going to have some, right, theorem that we're going to have to apply about limits, and we're going to use the one that is sequence-based. So, specifically, take a sequence that lives in the range of f, missing y, and let it converge to y. Right, so we're going to show that the limit of the output of the difference quotient evaluated at the sequence goes to where we want it to go. All right, and now let's define x sub n to be the outputs of f inverse. Okay. Now, note that those all land in I, and furthermore, y sub n is never equal to y, but y is equal to f of x, so the injectivity guarantees that x sub n is never equal to x, so the sequence lives in the interval I, but not including x. Okay, so note that since f inverse is assumed continuous, that means that the limit of x sub n is in fact x. Right, note I'm using the fact that the inverse is continuous. I'm stressing this. If I didn't know this going into this proof, I can't do anything at this point. Okay. Now, what does this mean? Well, 1 over the derivative is the limit of 1 over the difference quotient, right? But x sub n converges to x, and it's never equal to x. It's a sequence, so the limit of this is equal to the limit of that sequence. But how are all of these things defined, right? In terms of f inverse, they look like this. And, oh, hey, look. This is, like, really close to what I want. Indeed. We're done. Y sub n, that sequence converging to y, was arbitrarily chosen. Every one of those sequences converges to the same thing, so the limit has to exist. And specifically, the limit of this equaling that guarantees that f inverse is differentiable, and the formula for its derivative is precisely what we wanted it to be. And there we go. Beautiful. So no, a bit of work went into actually getting to a very quick and easy proof, honestly. Right? And note, the hard part was knowing that if I have a strictly increasing function, its inverse is continuous. And note, this is like instrumental in the proof. I don't know how you would circumvent doing this proof without knowing f inverse is continuous. Because you can't do it. Yeah. So, so it turns out that kind of the theorem that you would want to be true, which would just be like, oh, the derivative is non-zero, and then this holds. Turns out that actually it doesn't work that way, unfortunately. So what you got taught in calculus is kind of a little bit of a lie. It turns out that if you have an invertible function and it's differentiable, it's not necessarily going to be the case that its inverse is differentiable. There are some really weird examples I found on Math Stack Exchange that I couldn't really quite confirm, but basically, yeah, this formula is true, but there's a lot more hypotheses than just you've got a differentiable invertible function. Unfortunately, there's quite a bit more that you need in order to actually get this formula to hold. Right, so the question of whether the inverse function is differentiable, there's some hypotheses that are needed. Right. But not all is lost. In fact, there is a much stronger statement we can make here. So while this is true, and this is quite nice, there is actually a much more powerful result, and that is, of course, the titular theorem. Okay. But in order to do that, we first got to prove something quite nice. So we're getting to the inverse function theorem. We're almost to the fireworks factory. We just got one more thing to prove. All right. So let's say I have a non-degenerate interval, a point living in there, and a function that's continuous only at that point. If f of a is positive, then within the interval I can find another non-degenerate interval j that contains a, and f is strictly positive for every element inside there. No, f is not continuous everywhere. It's continuous at a single point. Then I can guarantee that there are points nearby that are all strictly positive. Ooh. Ooh, that's kind of neat. And, you done with that? Because I'm just going to keep doing it. Alright. So, set epsilon equal f of a. Note, hey, that's positive. I'm continuous. I got a delta. Nice. Alright, well, I need to create a non-degenerate interval. Alright, well, let j be I intersected with that. Note, by construction, A has to live in there. A is an I, and yeah, A... Plug A into this formula, and it works, so... Alright, I claim J is a non-degenerate interval. Pick two elements that live in there. Alright. And then let Z be something in between X and Y. Alright, well, X and Y are an I is an interval, so Z's got to be an I. Likewise, that's an interval, and X and Y are in there, so Z's got to be in there. Consequently, J is an interval. Now, as A is in I and I is non-degenerate, there is an element B in I that is either bigger than A or less than A. Alright, and we've done this song and dance before. Okay, in the former case, then we can find something in R that's between A and B, but also does not get any bigger than A plus delta. Alright. So that guarantees then, since J is an interval, that R is in J, and J is not equal to A, so there you go. And likewise, the same thing is met in the other case, where the R now we're going to find, instead of to the right of A, it's to the left of A, and instead of A plus delta, it'll be A minus delta. And that guarantees the non-degeneracy that we're looking for. Alright. Beautiful. So the only thing to verify now is that everything that is in J, f of x is actually strictly bigger than 0. Alright. Well, let x be in J. That means x is an I, and we also know that x minus a is less than delta. So, by the continuity, we know that f of x minus f of a is less than epsilon. Now, what does that mean? That means minus f of a, which is equal to negative epsilon, is strictly less than f of x minus f of a. Oh, hey. Add to both sides. Boom, f of x is greater than 0. Beautiful, right? Alright, cool. Alright, and now, equipped with this, we're able to prove the star of the show today, the inverse function theorem. So, this is the best version of the thing that you learned in calculus, which is that I have a function that's invertible and differentiable, its derivative is invertible, and there's a nice formula. Well, it turns out that it's not that cut and dry, but it's pretty close. So, let's say you have a non-degenerate interval, you have a point that lives in there, you've got a function that's differentiable, and furthermore, there's a point where its derivative is in fact continuous at that point, and the derivative is not equal to 0. Right. So as we noted, if you have a differentiable function, its derivative is not necessarily continuous everywhere, but for the most part it's continuous. Right? And furthermore, if the derivative is not equal to 0. If the derivative is equal to 0, then obviously there's no hope of this formula holding. Alright. So, if that is the case, then there exists a non-degenerate interval contained within I, that A lives in there, so that the range of the restriction of f is non-degenerate, the restriction of f is invertible, the restriction to J is inverse, is differentiable, and the formula we want holds. And there we go. So, kind of ugly looking, unfortunately, in terms of this, but basically it's saying that what you learned in calculus, that if I have a function that's differentiable invertible, its inverse is differentiable, and there's this beautiful formula. It's basically true, but it's not that you're assuming the function is invertible. What you're assuming is it's got a derivative, and its derivative is continuous at a point, and the derivative is not equal to 0. Then you can guarantee that you've got an inverse and things are good. So if you start out going with you've got a function that's differentiable and invertible, things get messy, unfortunately. There are these weirdo counterexamples that say that the theorems you want don't really hold, unfortunately. And all of the counterexamples that are out there are well beyond... Oh my god, there was one where you took like a copy of the integers and then you did a copy of like 1 over the integers and then you like matched terms, and it was disgusting. But anyway, so that is the inverse function theorem, and like all good, great theorems, Proof is super easy, because we already did all the work. By hypothesis, we know that f prime of a is greater than 0, or f prime of a is less than 0. Continuity of f at a then gives us a non-degenerate interval contained in I that contains a, and either the derivative is strictly positive or the derivative is strictly negative. And then we just apply the result we proved before that. That guarantees that things are good. The restriction function, the restriction of f to j, it gives me a range that is a non-degenerate interval. The restriction of f to j is invertible, and the inverse of that restriction is differentiable, and the formula behaves the way you want it to. And there we go. Beautiful. All right, so we have now covered most of the stuff we talked about differentiation. Now, however, some part of your brain might be kicking in and going, man, this whole course we're talking about calculus, you know what we really haven't talked about? We haven't done any trig yet. Yeah, sine and cosine really haven't shown up. I kind of pointed them out as an example, and I'm like, yeah, here's the thing. Well, it turns out that we can create sine and cosine from scratch, from analysis, from the least overbound property, but first, we need our good friend the integral. Ooh. That's where we're going to next. So, stay tuned.